Okay, so last time we saw that the BMS group is a group of asymptotic symmetries. That is a group of the symmetries of the asymptotic Minkowskian spacetimes. And what we saw was that the group B is actually a semi-direct product. So this admits an infinite dimensional group of super translations. And let's call it S. And then B modulo, which is a normal subgroup. So we can quotient and B mod. If I take the quotient, I get the Lorentz group. And so the structure is very similar to the Poincare group. Where I got the 4-dimensional translation subgroup, and if I take the quotient, I get the Lorentz group. So there's a parallel between this, right? That's what we saw. Okay? This is all clear. The difference is between that, whereas the space of translation is a 4-dimensional subgroup, the space of super translations is an infinite-dimensional subgroup of the BMS group. Now, I don't remember if we discussed this already, but it's also true that the BMS group admits in addition to all this structure, it turns out that it also admits a unique 4-dimensional normal subgroup of translations. And this subgroup is abelian, so let's call it subgroup, let's call it also T translations. And this is, of course, translations are in particular super translations, so this subgroup is a abelian subgroup. So it's, how are these obtained? Well, what we saw was that super translations, the super translations S, if I look at a Lie algebra, of super translation, then this consists of vector fields CA, and these were of the type, what notation we used, alpha or alpha times NA or F times NA or what were super translations denoted by?
Beta.
Beta. Where beta times NA. And we saw that beta is a conformally weighted scalar field. That is to say, if I went from QAB NA, if I went to Q prime AB, which is omega squared QAB and omega minus 1 NA, then since C doesn't change, that means that beta goes to omega times beta. That is why it has conformal weight 1. It rescales by omega. NA has conformal weight minus 1. And Q squared QAB has conformal weight 2. So we got this Lie algebra structure up here, and then the point was where it's conformal weight. And the idea now is to use the so-called preferred conformal frames. The reason we want to, I mean, it's not necessary. I can say what the translations are completely generally, but it takes longer to say this. So the simplest way to explain what the translations are is really to use a preferred conformal weight, because these are not functions, they actually depend on the choice of the conformal factor. So we just use a preferred conformal frame, and this is called the body frame, in which QAB is chosen to be a unit two-sphere metric. We saw that the two-sphere is a unique conformal structure, therefore given any metric, I can use a conformal factor, rescale it to obtain a unit two-sphere metric. By unit two-sphere metric, we mean a metric which is round. If you like, it is the scalar curve which is constant, and if it's a unit, then the scalar curve which is 2.
So that's what we are looking for, unit to sphere metric. Or you can introduce coordinates so that it just looks like d theta squared plus I squared theta d phi squared. So there's a preferred body frame up here. And now the statement is that in this frame, now we can just look at functions beta in this particular frame. And the statement is that since we have got a round metric, we just look at the first 4 y elements. So y0, 0, which is a constant, and y1 m's. So these betas, these are the translations. Did we already see this, or I forgot whether we had done this in the class already? No. Okay. So this is the space of translations up here. And then the statement is the following, that we might, the obvious question that you would like to ask is it true that there is a unique unit to sphere metric? So the question is of uniqueness. In other words, supposing I have a metric QAB, which is a body frame, so unit to sphere metric, and I make conformal transformation. Then of course in general this metric is not going to be a scalar curve which is not going to be constant, it's not a unit to sphere metric, but you can still ask that is it possible to choose omega such that Q prime AB is again a unit to sphere metric. And it turns out it's possible, these omegas are very special, and there is exactly a 3-parameter family. Of these omegas. I mean, to understand, you can just solve the equation, right? The scalar curve which is equal to 1 to scalar curve which is equal to 1, and then how many solutions there are. It's an elliptic equation of 2 sphere, and you find this. Geometrically, what is happening is the following. That in terms of Scri, there are several ways of saying it geometrically. In terms of Scri, if you just go to Minkowski space, then I can choose a rest frame. I can choose a t equal to constant surfaces, and I can just choose a unit time like vector, and then I can introduce coordinates. So in Minkowski space, I can just use t r theta phi, and then go to u r theta phi as usual, and therefore the metric just becomes du squared plus minus du squared minus times du dr plus r squared du omega squared. And we have done this many times, and we can conformally complete it. So this is a physical metric, sorry. So this is a physical metric, and so conformally complete it. ds squared equal to omega squared times dsi squared, and omega is again 1 upon r. And then you'll get a particular metric, and the statement is that the metric on Scri that you'll get, ds squared at Scri that you'll get, will be precisely d omega squared. So sine squared theta, so d theta squared plus sine squared theta d phi squared. We've seen this many times, so I'm not going into detail. You just substitute it up here and look at what the metric is, the intrinsic metric on, if you like. The full metric is going to be this plus twice d omega du, and if I pull back to Scri, then this term goes to 0 because omega is constant Scri. So you see that you get immediately a boundary frame. In other words, in Minkowski space, you just choose a particular unit time like vector, go to infinity, and then the metric is really the unit to sphere metric or Scri, you've got a boundary frame. But of course, immediately you would ask me, wait a minute, but who told you to choose this time translation? What if I choose a boosted time translations? So I could have used a boosted frame up here. So then I'll get here t prime, r prime, theta prime, phi prime. So we're just making a boost here. This is a Lorentz transformation up here. And again, I can do the same thing. And again, I will get a 2-sphere metric on Scri because it's again going to be Minkowski metric. So if I did that, then again I'll get Minkowski metric, and then I can go to ds. The completion of it, I can pull it back to Scri, and again it will look like
d theta squared plus sine square theta d phi squared.
With this now of theta and prime are prime, they are just the coordinates, angular coordinates of the boosted frame. And the statement is that this metric up here is again a round 2 sphere metric, but it's not the same as this round 2 sphere metric. They are going to be related to each other by confound factor, which is such that the two metrics are again round sphere. That means its confound factor is very highly constrained. So and since there are 3 rest frames you can choose, right? I mean, you're given a time translation, I can choose another time translation with the 3 parameter freedom. That 3 parameter freedom just boils down here. So the statement is that there is a freedom in choosing this unit 2 sphere metric, but you can check that this omega is such that the space of all these metrics share the same first 4 y lengths. Geometrically, again, it is clear what it means. Again, in Minkowski space, in the first metric, d by dt would be the vector field, which will be Na. In the next metric, d by dt prime would be the vector field, which will be this n prime A. So Na and n prime A are not the same. That can conformally rescale with respect to each other, and that is what is happening up here. Okay. So the statement is that, but then the statement is that they are very special, and now you can just calculate the y lengths of the first metric, and you'll find that the first 4 y lengths of the first metric are just linear combinations of the first 4 y lengths of the second metric. So if I take the first metric and choose the vector field Na, then and go to the second metric, I get a vector field n prime A. N prime A is just the restriction to scribe d by dt prime. But we know that n prime A is related to Na by some omega to the -1 factor up here, just in general. And so that's obvious, because what was a time translation, the time translation t prime in one frame looks like a mixture of a time translation and a space translation in the other frame, because I boosted with spinning that frame. And therefore there is this mixing up that happens. But the space of 4, every translation is back to another translation. They share the same, this is just means fixed Minkowski space, they share the same translations, and therefore the statement is that this 4-dimensional space is the same, but what you call pure times of translation and what you call pure space translation will depend on whether you started with this Minkowski space or whether we started with this Minkowski space. And that is why these first 4 y-lengths get mixed up. Okay? So this is what is happening, but they share the same y-lengths, and that is why the translation group is exactly the same. So what I've done here is to motivate the idea using what happens in Minkowski space, but at the end of the day, you can just solve for this omega such that both are unit 2 sphere metrics. Look at the y-lengths here, look at the y-lengths here, and find that the two are actually linear combinations of each other, and the geometrical reason is the one that I just gave. Any question? No? Is this okay? Okay. So there's a preferred translation subgroup. Where are we going? We're saying that there is actually preferred translation subgroup in here. And so, and that sits in the super translations up here. And the point was that it admits it's a unique 4-dimensional normal subgroup, and since it sits in the super translation, this is also normal and abelian commutative subgroup, and that is a group translation. And the point is that this is the group that we use as Scri to define energy and momentum. Remember, energy is the generator of time translation, momentum is the generator of space translation. Also, when you go to quantum field theory, for example, when you are looking at Hawking effect in curved space-times, in which you're got just a given stationary black hole, you give yourself a vacuum state on Scri minus, and you want to know what happens on Scri plus. Well, what do you mean by vacuum state of Scri minus or Scri plus? How do you construct these representations? Well, to do this representation, you need to decompose fields into positive and negative frequency parts, and again, this translation group on Scri enables you to do this. So this group is very important, this translation group, but the point is that it is not anyway, I mean, it is privileged, but on the other hand, there is the full symmetry group that you get is really the DMS group, and this translation group just sits among the super translations. So what we would like to understand now is what is this enlargement from translations to super translation? Like,
Yeah. So we have 3 parameters for this omega family because we have 3 different boosts, right? And then we have 4 YLMs because we have 4 translations. And those YLMs we get from the boost, so I'm kind of wondering where is this 3 to 4 coming from?
Yeah. So the statement is that it's just unit time. So if I take Minkowski space, and if I take the origin, and then I got light cone up here, and I got the mass shell. I mean, this is a unit hyperbolide. So here, like t dot t to the -1, and each of them gives you a rest frame because this is one time translation, this is another time translation, another time translation, etc. So the statement is that the freedom in the choice of omega is a 3-parameter freedom because we're just using unit to sphere rather than just any round to sphere. If I use any round to sphere, then I can also have the freedom of rescaling. I'll get 4 dimensions. But because I'm looking at unit to sphere, I get a 3-parameter freedom. So the statement is that the YLMs have nothing to do with this 3-parameter freedom to begin with. I just have this 3-parameter freedom, and then the statement is that that if I calculate the first 4 YLMs with respect to Q or Q prime, I get just the linear combinations of each other. So this 3-parameter freedom is distinct from this one. You give me any one, and then the translations with respect to that QAB would be given by these YLMs. You give me another T prime, then with respect to Q prime AB, I will get again some YLMs. These are functions of 2 sphere. The statement is that the 2 are just linear combinations of each other. So the 3-parameter and the 4-parameter are kind of distinct from each other. This is the freedom in the choice of the conformal frame, and these are the translations. So there's a boost and translation. That's the
that's completely separate from what's over there.
No, it's the same here. So please ask again.
Sure. So the basic thing is like on the second part of like the board, you're doing like that's all about boosts, right? Like, yeah. So then on the fourth part, like the third part, you're then going like there's also the 4 YLMs, which is separate.
Yeah. So but yeah. So the statement is that these is it possible to rescale? So the statement is that yes, there are 3-parameter family of such omegas. And then the statement is that, therefore I got 3-parameter family, so they is the thing. So, and this 3-parameter family the matrix QAD, which are unit to sphere matrix, they share the same for YLMs. Okay. Any other questions? Okay. So the point is that you have got this huge super translation group, and we also have the translations sitting in that super translation group up here. And as I was just saying, that group of translation is really important for us because physically we know that the energy is generated, is a Hamiltonian of the time translation, momentum of space translation, etc. So that is how it all, so that's why this is important. But now what we want to understand is really the enlargement from the Poincare group to the behaviors group. I think by now you are used to going back and forth between the group and the Lie algebra, so I'm not being very consistent. Sometimes I talk about groups, and very often in analysis we use just algebra, Lie algebra. It's just because it's easier, but you can just go back and forth between the group and the algebra. With algebra, the infinitesimal elements of the group, they are like the tangent vectors of the identity. So now we'd like to understand what is going on here. I mean, you know, on the one hand we got this infinite dimensional freedom. On the other hand, we do not, or we do also have a translation subgroup. So what is happening up here? So what is happening up here is the following. That I think I began explaining this last time. That from the physical space-time perspective, how does this arise? You see, we have seen so far really intrinsically at Scra. But now let's go back in the physical space-time, not just on Scra, not just on the boundary, but in the physical space-time, and let's understand how this freedom arises up here. So I think I told you last time already that the point is that our physical metric GAB is asymptotically flat. That implies, and this is going to be one of the homework problems, that implies that it looks like the Minkowski metric plus some terms of, let me just not put a hat, is Minkowski metric is eta value, so plus term of the 1 upon r, and these terms of the 1 upon r are of a specific type. Basically, I think we already did this. If you have scri, then I can take a cross section and translate it by this vector field NA. So I get one parallel family of cross section. I got the affine parameter u of NA, and I got the coordinates theta and phi, which go around up here. And therefore, I got a vector fields M A going like that, and a vector field M A going like that. M A and M bar A going like that. And then the statement was that, well, what we can do is, so these are u equal to constant surfaces. And then what we can do is, we can just take the other null normal. Now I'm space-time, not just on scri. So I can just do this other null normal. So this is our null normal NA. So maybe we should take it outward pointing. So that so both are future directed. This is NA and this is LA. Therefore, future parameter such that n dot n is equal to -1. And then we saw last time that we can just go along. Last time or the time before that, we can just introduce a tetrahedron by just using a geodesic propagation of LA. So I can just ask LA grad A and B equal to 0, and I'll get this LA vector field everywhere up here. And then I can drag coordinates along here by just asking LA grad A U is equal to 0, LA grad A theta equal to 0, LA grad A phi equal to 0. I just do that. And then I need to have a fourth coordinate, which I can just use to be omega. So in this little neighborhood, I got omega, theta, phi, and u as good coordinates up here. And our conditions of asymptotic flatness will immediately tell you that the space-time metric in these coordinates, the conformally completed metric in this coordinate at scri just looks like ds hat square is equal to minus du square, actually minus omega squared times du square plus twice du omega plus du omega. So space-time metric at scri looks like that. And then when you go inside, you acquire terms of the order of 1 upon r. But since you are lead dragging, you are parallel transporting these vectors and lead dragging the coordinates, these terms of the order of 1 upon r are of a specific type, and that you will see in the homework problem what type. I mean, it's a very generic thing. It just has, it has 7 functions because metric has in general 10 functions, and you are fixing some coordinates, so you're killing your coordinate freedom by 3 by saying that these are all null cones, both of the conformal metric and therefore also the physical metrics, as both are conformally related to each other. So you get a preferred coordinate system, and then you'll find that these terms have some specific form. But then, as I mentioned last time, I can just consider so that for this eta AB, I can write as minus dt squared plus dx squared, and dx squared plus d2 dy squared plus dz squared. But now what I can do is to make a certain angle-dependent translation. So if t goes to t plus a constant, that is a time translation, and under time translation the metric doesn't change. But if t goes to t plus a function of theta and phi, of course the metric is going to change under that thing. And therefore let's call it t goes to t prime. And for simplicity, let's just say x prime is equal to x, and y prime is equal to y, and z prime equal to z. Okay, we just make an angle-dependent time translation. Then again, we'll have a new metric, eta prime AB, which is minus dt prime squared plus plus squared. I'll get the new metric. And the statement is that you can just substitute here and check. It just has to do with the relation between the angular derivatives, d by d theta, d by d phi, and derivatives in the Cartesian coordinates, d by dx, d by dy, d by dz, d by dt. You will see that this is of the type, this is just equal to eta AB. So, So you'll find that this is just equal to. So this is equal to dx prime a dx prime b times that, and you'll see that this is the same as just dx a dx b times eta a b plus specific terms of the order 1 upon r, just substituting it here. So what I'm saying is the following, that asymptotic flatness, as we all knew, does imply that far away the metric looks like Minkowski metric plus 1 upon r correction. It does imply that. But the point is that this Minkowski metric is not unique. I can choose one Minkowski metric and show that this is asymptotically flat. But then you can come along and you can just define another Minkowski metric. Just make an angle dependent translation and then you'll produce another Minkowski metric, another flat metric. And since these two metrics differ only by 1 upon r, of course I can also write down therefore GAB to be equal to G prime AB. GAB equal to G prime AB. So is equal to eta prime AB plus terms of order 1 upon r. In other words, GAB was equal to eta AB plus order 1 upon r. But since eta and eta prime only differ by terms of order 1 upon r, then in particular this is also true. And the important thing is that this 1 upon r fall off is the same conditions. So you'll obtain here that they are of specific type, so same conditions on fall off. So those conditions which are of specific type, they are preserved. So what I'm saying is that given the physical metric, which is asymptotically flat, you can just expand it using another Minkowski metric, which is related to the first one by an angle dependent time translation, and therefore is not the same as the first one. And again, it is going to be admissible. And this is the freedom that you have. You see, first people would say that, wait a minute, physical space-time metric goes to Minkowski space-time metric plus 1 upon r. Then one would say, okay, if it goes to 1 upon r, of course the asymptotic symmetric group is the symmetric group of eta AB, which is a Poincare group. But what I just seen is that what you have given me is physical space-time. It's for me to find the Minkowski metric to which it approaches like 1 upon r. So you can approach eta AB or eta prime AB as 1 upon r. I got a Poincare group of eta AB, I also have a Poincare group of eta prime AB. So that would also be an asymptotic symmetry group. But since eta AB and eta prime AB are not equal to each other, if f is not a constant, if it's a function of theta and phi, and it can only be a function of theta and phi for all these things to work out, so it's really angle dependent translation up here. Therefore, the statement is that the asymptotic symmetric group will have to include the Poincare group with respect to eta, Poincare group with respect to eta prime, etc., etc. So we have to put together all this Poincare group, roughly how many? As many there as there are functions of theta and phi. That's what we put together, and that is exactly what the BMS group is. BMS group, I mean, I can make it precise, but at an intuitive level, BMS group is really a group that can be obtained by putting together harmoniously all the Poincare groups associated with flat metrics to which the physical metric approaches in the specified manner. Okay. And that is why asymptotic flatness actually does not give you a Poincare group, or gives you this. And the fact that these translations are angle dependent, it also shows immediately here, because these betas here are functions of only of theta and phi. So if you go to a body frame, then these betas are just functions now, because I've chosen a particular body frame, I don't have confounded freedom. So therefore in a body frame, I just have, in a given body frame, the super translations are arbitrary functions of theta and phi, whereas translations are just the first 4 y-lengths. So under the action of translations, this metric would not change. This metric would not change. None of these metrics will change. So all this Poincare group share the 4-dimensional translation subgroup. And that is why there is actually of the BMS group. And that is why there is so much freedom in the BMS group. I'm sorry, that is why there is a unique translation subgroup in the BMS group, because all these Poincare group have the same translations, but their Lorentz groups are different. See, within a Poincare group, let's suppose Poincare group of eta, a fixed flat metric, we're going to 4-parameter family of Lorentz groups. If you choose an origin, in Minkowski space-time, then I obtain a unique translation subgroup, unique Lorentz subgroup, right? Namely, the Lorentz transformations are hyperbolic rotations which leave this point invariant. Right? So given any one of them, so translations are, they don't leave any point invariant, they go like that. It's a time translation or space translations. They don't leave any point invariant. But each Lorentz transform, each Lorentz subgroup of the Poincare group leaves one point invariant. And if I go from one point O, origin O to origin O prime, here I got a Lorentz group L, and here I'll get a Lorentz group LO and LO prime. These are two different, and they are related to each other by translation, as usual. This is a standard thing that happens in Euclidean space, right? If I take Euclidean space and if I look at the group of SO3 rotations, rotation always leaves some fixed point invariant, right? So there's an origin. So the SO3 subgroup about this origin is different from SO3 subgroup about this origin. Two are related to each other by translation, this translation up here. And that is why angular momentum about this origin is equal to the angular momentum about this origin plus the skew product or cross product of the 3 momentum multiplied by this translation that I have done up here. So they're all intertwined, and there are 4-parameter family of Lorentz subgroup. Within any Poincare group, there are 4-parameter family of Lorentz subgroups. Within BMS group, we have an infinite dimensional, as many as are functions of theta and phi, parameter family, and infinite dimensional. Of Lorentz subgroups. In the Poincare case, these Lorentz subgroups are all going to be related to each other by a translation. This is the translation that I'm making. They are related to each other by that translation. They are related by a translation. And because we got 4-parameter family of translations, we got 4-parameter family of such subgroups. Within the BMS group, we have infinite dimensional family of Lorentz subgroups, and they are related to each other by super translations. So what is the lesson we're learning here? The lesson we're learning here is that translations are canonical. The 4-dimensional translation subgroup is canonical in the BMS group. We see it abstractly from the group theoretical considerations, and we see it in the physical space-time, because in the physical space-time, BMS group is putting together the Poincare groups of eta, eta prime, eta double prime, etc., related to each other by a angle-dependent translation, and you can just check that the translation group of eta is the same as the translation group of eta prime, but the Lorentz groups of eta are different from Lorentz groups of eta prime. And the state, so these angle-dependent translations, and these angle-dependent translations, there are Lorentz group associated with this. These are the different ones, and that is why we got an enlargement of the symmetry group from the Poincare group to the BMS group. What this means is the following. In terms of constant quantities, as I just mentioned, there is no problem with energy and momentum, but there is a problem with angular momentum. Namely, the notion of angular momentum is tied to the Lorentz group. In Minkowski space-time, there is an angular momentum that is defined about an origin. So if you like, if I define angular momentum about one origin or another origin, they are related to each other by the translation that relates the origin and the 3 momentum. You know, the usual. The angular momentum is always given in non-relativistic mechanics. Angular momentum is given by r cross p. If I make a translation, r goes to r plus or r minus this translation. Right? This I'm saying, here's a slight remark up here. In ordinary non-relativistic mechanics, I can take an origin, and then the angular momentum L is r cross p. And if I take another origin, O prime, the two are related to each other by translation, then with respect to O prime, the angular momentum with respect to O prime will be equal to r prime cross p. But r prime, if this is r, given any point, this is r coordinate, this is r prime coordinate, r prime vector. Therefore, r prime is r is equal to t plus r prime, and therefore r prime is given by so we just substitute here, right? So what we see here is that if I get t plus r prime is equal to r. So if I just substitute for r prime here, I will get here r minus t cross p. So that is equal to the original angular momentum r cross p minus the translation times the three-dimensional momentum. So this is the usual law of transformation of the angular momentum. And in Minkowski space, the same thing is true. These translations are replaced by space-time translations, and these rotations, if you like, the angular momentum is now six-dimensional object, right? Because this is three-dimensional. Angular momentum has three boosts, and relativistic angular momentum has three boosts and three rotations of six-dimensional object, and you get a similar transformation law here. But in the BMS case, we have to think much harder about what we mean by angular momentum, because we have got this infinite dimensional freedom. And that is an issue which is, there's a lot of progress on it, we understand a lot of it, but it's much more technical. So if you're interested, I can give you references where you can read about it, but we're not going to discuss it any further. Are there any questions what is happening about the enlargement of the Poincare group and its effects? The notion of translations and therefore energy momentum, no problem. The notion of Lorentz subgroup, the number of Lorentz subgroups is enlarged from 4-parameter family to infinite parameter family, and therefore the notion of angular momentum is also enlarged, and one has to come to grips with it, which is kind of a topic in itself, which we are not discussing right now. Any questions? Okay, so then let's go on to the next topic. And the next topic is, this is all nice and good. We understood the universal structure, we understood the symmetries, we understood the group of symmetries and so on. Now what we would like to do is to understand where is radiation. Since so far we have restricted ourselves to the universal structure, and the universal structure is common to all asymptotically Minkowskian space-time. So within this paradigm, within this universal structure, you cannot see radiation, because this structure is common to stationary space-time like Schwarzschild and radiating space-time. So this doesn't carry in any information about radiation, or even Minkowski space-time will have the same universal structure as Scrap. So where is radiation? Now this is, I think, one of the most beautiful interplays about geometry and physics, perhaps the most beautiful we discussed so far, and it has to do with the fact that from the point of view of geometry, we saw that the first order structure, infinity, is given by the metric and then the normal. What would be the next order structure at infinity? Well, typically from the point of geometry, I got metric, then the next order structure is the derivative operator, and the next order structure is a curvature. That's how we proceed up here. So the next order structure would be a connection on Scrap. And it turns out that the information about gravity and radiation, not only in the linearized theory, but also in full general relativity, is entirely encoded in this derivative operators or these connections on Scrap. And by the way, those who know about gauge theories, this is also true for non-abelian gauge theories. The entire information about the connections, about the radiation, radiative modes, or true degrees of freedom are encoded in the connection at Scrap. So this is what we will now want to do. Radiative degrees of freedom. Okay. So what are the radiative degrees of freedom of Scrap? How are we going to get it? So what we saw was that, what do we have for Scrap? is a boundary of space-time manifold. It's a boundary of space-time manifold, and we saw that if you look at in the space-time language, in terms of conformably rescaled space-time, MGAP, whereas in the SCRI, this topology is S2 cross R, it is null, it's a null manifold here, and we saw that the null normal NA to SCRI A satisfies. So the null normal NA is defined to be equal to GAB grad B omega. Omega is 0 on SCRI, therefore grad B omega is a covariant normal. I raise the index, I get the null normal. And we saw that this, we're using divergence-free conformal frames. And in those conformal frames, the null normal is covariantly constant on SCRI. So here is SCRI, three-dimensional manifold. Here is space-time interior up here. And what I can do is to choose a cross-section. Let's call it cross-section C up here. If I give this cross-section C, then I got a metric on SCRI. So this is a side remark. We're getting a metric on SCRI, which has significance 0 plus plus, and therefore it's not really invertible. But I can define the inverse by saying any QAD will be said to be inverse but this inverse is of course ambiguous. This is typically problem of inverting the non-degenerate metric up here. And therefore QAB will be said to be inverse if it satisfies QAC. QBD is again equal to QCD. So we say that this is what we mean by inverse. But of course we're going to freedom, this ambiguity. If I take QAB goes to QAB plus any vector tangent to SCRI times NB, then this also satisfies the condition up here. Let's call it Q prime AB. Okay, QAB goes to Q prime AB, then this is also the inverse. Q prime AB is also satisfied the condition QAB, QAC, QBD, because this N is going to hit one of the two metrics, and therefore it's going to kill it. And so there's an ambiguity. That's a usual thing that we got an ambiguity about the inverse up here. All right. Now, but if I give myself a cross section, then I can define as usual my two-sphere metric on this cross section. This is the metric on the cross section, and the statement is that this SAB then is one of these QABs. SAB is the inverse for which where L is the covariant normal to the cross section with this graph. That means, if you like, if I got vectors here MA and M bar A, then LA equal to 0. So LA is any vector which is tangential to the cross section. So I do have a nice notion of covariant normal to cross section, and given a covariant normal, I can pick out a canonical inverse. This we have been doing quite a bit in the case of the isolated horizons, which is also null surface. Sometimes we chose a cross section and define a metric SAB, which is really a metric plus plus now because just living with the cross section. Or we can live with entire SCRI and we can think about these degenerate metrics. The statement is that SAB is just equal to QAB, pull back to the cross section, and SAB
is equal to that null normal which satisfies this condition on the cross section C up here. And therefore, what I'm just recalling for you what we've learned already when we studied non-expanding horizons and weakly isolated horizons. Remember that what was non-expanding horizon? It is a null-free surface such that the expansion of the vector field, which is tangential, which is the null normal, if you like, of the free surface, vanished. In the case of the non-expanding horizons, we had this picture in mind, which was coming from, say, for example, Schwarzschild geometry. If I look at Schwarzschild geometry, I got scri plus, scri minus, and I got these horizons. And what we had in mind was this. The expanding horizon was this, and the vector that was tangential to this was L. Now what we have in mind is scri, and the vector that is tangential to scri is N. So really what is happening is just that we are swapping L and N. That's what happened. That was happening going to scri here. There L was expansion free. Now we want to ask, is N expansion free? But we already saw that in fact grad A and A is equal to 0. This implies that the expansion of N, which is just equal to SAB or QAB, grad A and B, that is just equal to 0, because grad A and B itself is equal to 0, so of course this is equal to 0. This all the equations I'm writing now are at scri, and therefore I'm not writing hex signs up here. So we got this expansion, and the shear of this was given by SAM, SBM, minus 1/2 SAB, SMN. So it's a trace-free part of the derivative. But since the derivative is 0, this whole thing is 0, so this is 0. So in particular, we know that scri is actually a non-expanding, mathematically, is a non-expanding horizon, but of the conformal geometry. Physically, they are very different from each other. Physically, the weakly isolated horizons and the non-expanding horizons, which we use for black holes, were properties of physical geometry. Physical metric is just not well defined in scri at all. And therefore, I'm not talking about properties of the physical geometry, I'm talking about properties of the conformally rescaled geometry. And the statement is that with respect to the conformally rescaled geometry, scri is null, is S2 cross R, is null, and is shear free and expansion free. So of course it is a scri is mathematically, I say mathematical because it is with respect to the conformally rescaled geometry. This is mathematically a non-expanding horizon. And furthermore, remember that for this L vector field, we immediately saw that there is a derivative operator D on scri because it was a non-expanding. In fact, as soon as it was a non-expanding horizon, there is a derivative operator D on scri. A D on the non-expanding horizon. Remember, this was the case that on the non-expanding horizon, we could just pull back the space-time derivative operator and get a derivative operator here. It was in your homework problem, you showed that. There's a well-defined derivative operator on the non-expanding horizon. Therefore, I can take this scri, this derivative operator D, graph on scri, and I pull it back, and I obtain dA. This is on scri. This is a torsion-free derivative operator on scri. So it's a very special non-expanding horizon. Not only have the shear and the expansion 0, but it's also geodesic, because it's also true that if I take the acceleration, NA, grad A and B, that is also 0, because grad A and B is 0, therefore all these things are 0. So it's also geodesic. So therefore scri is expansion free, non-expanding.
shear free, and geodesic vector field. It's a very special vector field. It's a very special kind of non-expanding horizon. You can quickly check there's also a weakly isolated horizon, because the weakly isolated horizon was defined as follows. You take dA, LB, and just because it was a non-expanding horizon, we saw that this was of the type omega A, LB, and omega was called the rotation one form. And then what we get up here is that L of omega A. If this was equal to 0, then we call it weakly isolated horizon. But for Scry, we know that grad A and B itself is equal to 0. So therefore, there is an additional property that if I take grad A and B and I pull back on this index on Scry, I will obtain this to be equal to 0. Right? Is 0 as Scry, but this object is the same as grad A and B. So this object is the same as dA and B. This object is the same as dA and B on Scry, and therefore this dA and B is just equal to 0. That means that omega A, the rotation one form, is 0. So of course it is trivially true that En of omega equal to 0, because the rotation one form itself is 0. So it's a very special non-expanding horizon, namely it is geodesic, and in addition to that, the rotation one form is 0, and therefore it's in particular weakly isolated horizon. Again, physically, this has nothing to do with black holes, but mathematically we can take on all the properties of the non-expanding horizon we discussed in the class. And that is why this is so important. Right? What we had done before for the non-expanding horizon, we would spend quite some time in understanding the details. It took a little longer than to finish black holes than what I had anticipated. But it's okay, because suddenly now that machinery comes to our help, and what we know is that Scry admits, given a conformal completion, Scry admits not only QAB and A, and a derivative operator D. So it's a torsion-free derivative operator. Such that this is equal to 0 and B and B equal to 0. Again, almost always, I am always at Scry, therefore I'm not putting the hats equation up here. In an equation like this, I put hat because I was in space-time and I was pulling back to Scry. That is why I am putting hats up here. But here, I'm not putting hats explicitly just because everything is at Scry now. So I get this derivative operator. Given any conformal completion, I get this derivative operator. Now, as we saw before, if in fact this metric was non-degenerate, if it was plus 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 or minus plus plus, then D would be unique. Then that is really determined by the metric. The metric was the universal structure, we're done. So therefore, D is part of the universal structure. But it's precisely because the metric is degenerate, there are infinitely many derivative operators which satisfy this condition. So these two conditions do not determine the derivative operator. There is infinite freedom in the choice of the derivative operator. These conditions appear. And that freedom is where the information about gravitational waves, gravitational radiation lies. Okay. So it's a very beautiful thing that Scry is null, there is a universal structure, but precisely because the metric is degenerate, the derivative operator is not unique. So you give me a space-time, I'll get one derivative operator. You give me another space-time, I'll get another derivative operator. I don't have to get the same derivative operator, even though both these derivative operators have to kill both Q and N. Okay. So that is the main point up here. And so now what we have to ask is, so the claim, I mean, it's not obvious, that's what we are going to see this time and next time. Hopefully we'll finish our discussion of gravitational waves next time. So the claim is that the information about radiation, radiative degrees of freedom, or in physics one often says 2 degrees of freedom. Now this is full general relativity. In Minkowski space field theories and quantum field theories, you already know how to take out the two degrees of freedom. For example, for the photon field or for the linearized gravitational field, you can do a transverse traceless decomposition, and you know that there are 2 modes which define the photons, right? The 2 polarization states appear. Here we're talking about nonlinear full general relativity. And still, because we can go to Scry, we can actually extract the information about the radiative degrees of freedom. Within the space-time, I cannot. This is the point that I emphasize many, many times. But at Scry, we can. And they are the radiative degrees of freedom lie in this D. That is what we now want to see. So now what we want to see is, well, how many connections are there on Scry? How many torsion-free derivative operators are there on Scry which actually kill a given QAB NA pair? So for a little while, let's not worry about the conformal rescaling freedom. Well, we will. But let's suppose that QAB and N is actually fixed on Scry. Suppose we are given a conformal frame. I'm not saying what frame it is. It could be a Bondi frame, but it doesn't have to be a Bondi frame. Supposing we are given a conformal frame, the QAB and A and Scry. Supposing we are given this once and for all, right? Do I fix this thing? Then the question we would like to ask is, how many D's are there satisfying these 2 conditions? Because those will be the potential degrees of freedom which can vary from one space-time to another. They can contain the radiative information. Are there any questions? You see where we are going, right? So, how many derivative operators there? That's what you now want to understand. So, for this, it's best to go back to where to understand these 2 conditions. And for this, it's best to go back to this picture that we have of Scry, H2 cross R. So, I got this given, the Scry is given to us, and I got this vector field NA given to everywhere. And as we saw, we can go to the base space, which we just call S, the base space up here, which is topology S2. Right? And every point up here is a generator. This is a space of generators. And we get the projection mapping, the obvious projection mapping, from here to here. Now the point is that because these 2 properties are so strong, the action of all derivative operators is highly constrained. I mean, the derivative operator is not arbitrary, but it's highly constrained. So we want to understand how constrained it is. And what I can do is, I can consider on Scry a vector field, or can consider one form. Let's call it one form omega A on Scry, such that omega A and A equal to 0, and Lien omega equal to 0. So such an omega, those of you who know different geometry and pullbacks, clearly it just starts with one form here, and I put it back, and I will get a one form on Scry. So there's a one-to-one correspondence between such one forms and the one forms up here. But we also know that we get the metric QAB, and this metric QAB we're seeing is a pullback of a metric up here, because QAB satisfies QAB and A, QAB. We don't have it here. So we also know that QAB and A equal to 0, and QAB Ln of QAB equal to 0 on scribe. Because of this, we have seen before, that means that the degenerate metric here is really pulled back of some metric up from here. But now, the statement is that given this derivative operator d bar, the q bar up here, there is of course a derivative operator which kills it, which is torsion free. But this is of course a non-degenerate metric. Therefore, this operator is unique. So on such one forms, I know what the derivative operator is here. And so you would imagine that on such one forms, the all derivative operators here should agree, because this derivative operators up here satisfy these conditions. Therefore, if I get a one form which is pulled back up here, then there is a derivative operator here. The action of this derivative operator here could be just pulled back, and I will get the action of the derivative operator there. And this is correct. And the reason is because I can write down now dA omega b as a symmetric part plus the antisymmetric part on scribe. It's not very profound. But now the interesting thing is that the symmetric part, as you all know, is actually Lie of some vector field. Let me call it, what can I call it? Let me call it omega under bar A, some vector field of QAB, where omega under bar A is just equal to QAB times omega B. So I just raise the index with some derivative operator up here. Now, with some inverse metric up here, and if I take this derivative operator, you can expand it out, and you will see that you will just get this term and nothing more. But now this omega bar, to begin with, is a little bit ambiguous, right? Because we just saw that omega, I can choose another omega bar, which is q prime AB times omega B. And q prime AB is this ambiguity in the notion of q prime AB. I can always add to QAB a TA and B. So therefore, q prime AB will be equal to, so this object will be equal to omega A QAB plus TA and B times omega B. Right? Because there's an ambiguity here, and this T is an ambiguity. So I'm saying that is this I can do this, but is this operation well defined? Well, to raise the index, I have a QAB, and now what I have to show is that no matter which QAB I obtain, I use, this quantity will be equal to this quantity. That's what I have to show. Well, what is the freedom in omega up here? The freedom in omega up here is just that freedom up here. But when n hits omega, I get 0, because by definition, that is what omega was. Therefore, I just get here omega A plus TB and B times omega B. But now you all know that Lie of any function times n of QAB is 0. We have seen this many times. This is like a super translation, if you like. We have seen this many times up here. Lie of any function of f times Q. Shall I show it again, or you are happy with it? No, I guess we're not happy with it. Okay, so why is this the case? Well, this is because this Lie derivative is given by f times Ln of QAB plus QAM dBf times Nn plus QMB dF times Nn. But Ln of QAB is 0, n times Q is 0, n times Q is 0. Therefore, this is equal to 0. Therefore, the statement is that this term, the statement is that there is an ambiguity in what I mean by raising the index of omega, one form omega with this metric Q. But that ambiguity just adds to this omega a multiple of n. And I'm sorry, I think I wrote something wrong here, that's why everybody's puzzled. This is equal to omega A and then TB omega B times NA. So when n hits this, I get 0. I get here T hits this times n. That is the term that I got here. Is it okay? Okay. So the statement is that there is an ambiguity in raising the index of this one form But that ambiguity just adds to this omega a multiple of n. But a multiple of n just Lie drags q. Therefore, this ambiguity washes out in this Lie derivative. So no matter what metric I choose, no matter what inverse metric I choose to raise this index, I will always get that this is equal to this. And then plus I get the dA omega b. But you all know that Lie derivatives don't depend on the derivative operator. And you all know that the exterior derivatives don't depend on the derivative operator. So this implies that because this can be written like that, dA omega b equal to d prime a omega b in our collection. So let me just finish in 1 minute. So what we have seen so far is just the following. That we are interested in derivative operators which satisfy these conditions on QA, B, and N on Scra. And we're asking how many are there. So to understand that, we want to know what is it that these D's have to satisfy. Of course, they have to satisfy these two conditions. But it's a nice implication of this condition, which is very convenient to use, is the following. That if you give me a one form here, such that it is transverse and is Lie dragged by omega, then the operation of D on this is the same as the operation of any other D on this in our collection which satisfies this. And just geometrically, this is more or less obvious because any omega which satisfies this is really lives downstairs here. It's a pullback of some omega bar from here. And here I got a metric QAB, and therefore I got a unique derivative operator D, which kills this metric QAB. So I just take this D and operate on omega, and I put it back. And when I did that, I get some field, and that is the action of the any derivative operator on omega. So therefore the freedom is just very simple. Freedom in the choice of it's just I have to specify what is dA/LB for some LB, which is such that LB is not equal to 0, so let's say equal to 1 or minus 1. So suppose if you give me what is the action the derivative operator of any L, which is not transverse to N, right, which is kind of dual to N, then in fact the action of the derivative operator is completely determinate. Because what we are saying is that on vectors which are sort of linear combinations of M and M bar, the derivative operator action is completely known. These are covectors, sorry, let me call it covectors, M and M bar. The derivative operator action is completely known up here, so I should not add an arrow. So take M A M bar B, A, such that N A M A equal to 0. So this is, N is now omega. I know what the derivative our operator does. So the cotangent space here is 3-dimensional. I got MM bar and I got a third dimension. In the third dimension, I'm just choosing it to be L, so that L dot N is not equal to 0, and I just choose it to be equal to minus 1, doesn't matter. I can put any function up here. So if you give me any, if you know what D does to any of these covectors, I know D everywhere. Normally, I have to tell you what D does to every covector. But the action of all these Ds, or covectors which are transversal, is the same. And therefore, it suffices to tell you what the action is on just one this covector. And this is what we're going to now explore, how much freedom there is. And we'll see that, ultimately we'll see that there are only 2 degrees of freedom per point of Scra at the end in these connections. And those degrees of freedom are the true degrees of freedom of the gravitational field, or of the graviton, or of the graviton fulgent GR, not linearized theory.